first content is phase or micro constraint in the steel and behavior, right? Okay, anyways, so up to this class you understood why we are doing heat treatment, huh? Right? But what is our objective? So we have many objectives. One is to change the mechanical properties. It may be to increase the ductility, to increase the strength, or to increase the hardness value, right? Or other things is like you can reduce the internal stresses also, which are generated due to mechanical working. Suppose some residual stress is there, you can remove them also. That means to remove the residual stresses, right? Because residual stresses are not good during application. It may undergo stress corrosion cracking sometimes. And also we are doing heat treatment to refine the grain size. You understood, if the grain size will be finer, the strength will be more, toughness will be more. So by doing heat treatment you can refine the grain size. You can make the grain size smaller. And there are other advantages. Sometimes we increase the electrical conductivity. For example, if you remember during annealing process, full annealing kind of thing, the recovery occurs. First stage is recovery, second stage is recrystallization, third is grain growth. So during recovery stage, a lot of dislocation get annihilated and the electrical conductivity improves in that condition. This is one of the important questions for GATE. Sometimes they ask what exactly happened during recovery stage and what benefit you can get. So the benefit of recovery stage is what? You can enhance the electrical conductivity. Why this is happening? Because lot of dislocation are getting annihilated. Annihilated means they get disappeared. You know, I think you know the concepts, polygonization and all, right? Maybe you know. You studied this in like maybe in mechanical behavior. You don't know. Annealing, you don't know that after cold working we always do annealing. So what happens during recovery? You don't know these things. Okay, anyway. Okay, I will discuss that in coming lecture otherwise. Okay, fine. There are three stages: recovery, then recrystallization, and grain growth. Recovery stage means defects will get annihilated, mostly dislocation get disappear. In recrystallization stage, new strain-free grains form. The grains are free of strain. That means it is more ductile. Okay. And last is grain growth. The grain will become more bigger. That means it is more ductile again. So basically, this annealing is done after cold working, right? Why this is done after cold working? To remove residual, but you can again flatten, fine. But the point is, you can say once cold working is done, and you further want to plastically deform it, or you want to reduce the thickness further, you cannot do that unless until you do annealing. Why? Because it got strain hardened. After cold working, the material got strain hardened. Automatically the hardness will increase to a large extent. Why? Because lot of dislocation will generate. During cold working, lot of dislocation will generate. And they cannot be annihilated. But if you are doing hot working, hot rolling for example, during hot rolling, dynamic recovery will take place. Or dynamic recrystallization also takes place. Right? Dynamic means you are doing rolling. So material becomes strain hardened. Why? Lot of dislocation is generating, right? Due to deformation. But automatically it is also getting recovered. Recovered means dislocation also get disappears. Generation disappears. Generation disappears. Because temperature is available already during hot rolling. But in cold rolling, temperature is not available much. Thermal energy is not available. No? Only you are deforming plastically. Because to do recovery, to do recrystallization, to do grain growth, you need temperature, high temperature. So that is the concept of dynamic recovery. No? Dynamic recovery means during hot working, dynamic recovery occurs automatically. Strain hardening, dynamic recovery. Strain hardening, but that means it is balancing. But cold working, only strain hardening will occur. No recovery, no recrystallization, no grain growth. That's why we are doing annealing. Okay. Do you understood this part or it is going above your head? Okay, fine. Anyways, so you understood. So what is the objective of heat treatment? So I mean to say, we are doing heat treatment so that we can generate some kind of phase which will enhance the property, or we can generate some kind of microstructure which will enhance the property. What? Mechanical property basically. That's why, because most of the heat treatment are done on steel. Anybody remember why we do not do heat treatment for copper? I told once, I remember. Okay, how many of you can answer? If there will be a question, to enhance the mechanical property, why we are not doing heat treatment on copper, but we are doing heat treatment on steel. Okay, don't answer. I know you. I want you people to raise hand at least. Raise a hand. Okay, 1, 2. You cannot do also heat treatment on pure aluminium, right? It will not give you enhanced property. Why? ये चौधरी का है. What you are doing? See, the main important reason is steel is the material which can show phase transformation behavior or allotropism, whatever you are saying. If you change the temperature, the phase will change. That's why. But aluminium, you heat the aluminium from room temperature. At high temperature also FCC, low temperature also FCC. But if you heat the steel, somewhere it becomes already BCC, 400 cubic. High temperature it becomes FCC. If you apply pressure, sometimes it may become FCP. And if you also do, sometimes it may become BCT. Right? So lot of phase change can be done in steel. And each phase will decide the property. Because each phase behavior is different. BCT behavior is different, BCC behavior is different, FCC behavior is different, right? HCP behavior, right? All phases are different in behavior. That can be done in steel or iron, but not possible in case of aluminium. Similarly, copper room temperature phase is FCC. You heat it to high temperature up to melting point also. Same FCC structure will be there. So crystal structure is not changing, so property will not change. In the first lecture, that's why I discussed material tetrahedron. If you can able to change the structure, you can able to change the property, and that will hamper the performance at the end. And for that you have to do processing. Heat treatment is a processing. Is it okay or? So you have to remember, this is a very important line. If you don't have any option to do heat treatment, but still you want to enhance the property, suppose enhance the hardness, enhance the toughness, or enhance the strength, what can be done? What can be done? Go for mechanical working. Just roll it, cold roll it. It will become strain hardened. So hardness will increase. Grain size reduce, but to do grain size reduction, you need to put energy into it. Again, thermal treatment need to be done. Whether it is recrystallization or whether it is normal quenching or maybe normal cooling, normalizing, that is normalizing. You have to give thermal energy, no? Heat treatment. You understand my point? Suppose there is a question, you have copper metal and you want to increase the hardness, strength, what can be done? Go for mechanical working. Mechanical working means not hot rolling. You have to go for cold rolling then that time. It will become strain hardened automatically. So why we are not preferring in case of steel? Because anyhow we are rolling it anyway. But we are not preferring because heat treatment is easy treatment process, easy process. Only give thermal energy. But rolling means you have to install a machine, you have to roll it. It is very expensive, of course. You understood my point? So this is interesting. Okay. You may get a question like this. Why, if you have a pure aluminum, how can you improve the hardness or strength without doing any heat treatment? Even if you are doing heat treatment, what will happen? Nothing will happen. But you should not get confused. You can reduce the grain size by doing heat treatment. That can be done. That can be done. Pure copper, pure aluminum, if you are giving heat treatment, you are cooling at a very fast rate, you can refine the grain. That can be done. But hardness, strength, you cannot achieve so high. Why? Because they are already FCC. You know that FCC metal is very ductile. And FCC metal don't have any ductile to brittle transition temperature. You know this thing? You have any idea ductile to brittle transition? Huh? Ductile to brittle transition means the material behavior also changes upon temperature. If you are reducing the temperature from room temperature to low temperature, towards sub-zero, maybe minus 10 degree, minus 30, minus 40. Suppose you are using a metal here, you are taking the same metal to Europe now or to Russia now, a very cold country. Europe it's fine, now Europe is also get heated up, you know. They are using AC, first time they are using AC in their home because of global warming. Or anyway, you take it to Russia for example, or to Antarctica. Temperature will be minus 30, right? So here temperature is how much? Plus 35 or plus 40 maybe. Then minus 30. So there is a sudden change in temperature. So your material is ductile here, but if you take to low temperature, it becomes brittle. Right? So that is called ductile to brittle transition. But if it is a FCC metal, interesting, it will not show any sharp transition temperature. It will behave ductile. Even if you are lowering the temperature, it will behave as ductile. Steel. Titanium is HCP actually. Titanium ship was earlier it is BCC structure. That is the problem. It was not FCC actually. It was BCC. They don't know at that time. After that failure, they start studying why it happens. That is the main cause of study of this DPT. Okay. But if steel is BCC, body centered cubic, there is a sharp decline in the brittle. That means the brittleness will improve suddenly. Sudden, like you take it to minus 10 degrees centigrade, it will become brittle and it will break. Suddenly it will break. You understand the point? So anyway, you have to remember, FCC metal is very good always. Why? And you know that. You know the sleep system. Shall I go into that, or you know the sleep system, sleep direction? Okay. Anyway. Okay, fine. So still, since we are dealing with steel, so what are the phases? Can I write quickly? Can you people write also? Okay, write. Austenite. Then the martensite. These are phase and micro constituents. Huh? Perlite. Benite. Okay. Ferrite, austenite, martensite, perlite, benite. Cementite. Very good. Sometimes carbon will be there as a graphite maybe. But anyways, these are important phase or micro constituents. Huh? Ladyburite. Okay. Ladyburite. Okay, fine. Ladyburite. So this is micro constituent. Fine. This is micro constituent basically. This is also micro constituent. Other are basically phases. Huh? Perlite is a micro constituent because it is not a single phase. It is a mixture of phase. Ferrite and cementite. Benite is also a mixture of phase. Okay, mixture of iron carbide and ferrite. Okay, and ladyburite is also a mixture of phase. Austenite plus cementite. So that's why it is not a mixture of phase. You can say it is a micro constituent. Okay, fine. But if it is a single phase, you can say it is a phase. Better, always. In interview, they ask simple questions. What is ferrite? Can you answer? How many of you can confidently answer what is ferrite? Single phase? What? Only it's a single phase. It is having this structure. But first of all, you have to define it. No? What is ferrite? It is a solid solution. You forget everything. It is a solid solution. No? Ferrite is a solid solution of carbon in alpha iron. Because iron is a pure element, the moment you add carbon into it, it becomes alpha ferrite basically. So it is a solid solution. Solid solution means carbon is a solute and iron is a solvent. And where the solute is going? To the interstitial sites, either octahedral void or tetrahedral voids. Right? Depend upon the size of the void. Right? Basically it goes to octahedral voids most of the cases. Why it is going into octahedral? Because size may be bigger. And sometimes what happens, if it is going to octahedral void, strain in the lattice will be less. These are the two main points. You have to always remember. Okay. Fine. So what is a ferrite? Ferrite is a interstitial solid solution of carbon in alpha iron. Similarly, what is an austenite? It is also again interstitial solid solution of carbon in gamma iron. Okay. Fine. Martensite. Yeah, you are right. Supersedial solid solution of carbon in what? BCT iron, you can say, body center tetragonal kind of iron. So what are the crystal structures I can write? BCC, this is FCC, This is DCT. Sometimes it shows HCP also. Some cases. Perlite means mixture, na? BCC plus Fe3C. Or actually Fe3C is what? Complex orthonomic, not orthonomic. It is complex. It is not simple compound, it is a very complex structure. Complex orthonomic. Then vanite is same BCC, ferrite plus any same complex orthonomic or something else it may be. It depends on, it is iron carbide actually. Sometimes epsilon carbide will be there. Epsilon carbide, you know, there is Fe3C, and what is the difference between epsilon carbide and cementite? One is Fe3C, one is Fe2.4C, I remember. Can you check? What is the formula of epsilon carbide? Cementite orthonomic. And ladybird FCC plus orthonomic. You can see different crystal structure, right? So different properties they have, of course. Fine. Simple. If you can able to change the structure, you can change the property. So all the structure are different, so property will be different. Suppose you have a same steel having martensite, you have a same steel having ferrite. So property will be different. Steel may be same, composition may be same, but structure is different. Which one will be more harder and stronger? BCT1 or BCC1? BCT1, because martensite will be there, right? That is the reason why it is very hard and brittle. You are getting my point, last people? Is it okay? Yeah, what is epsilon carbide formula? Fe2.4C, no? Fe2.4. Yeah. Fine. Okay, behavior. If you want to see the behavior, so the behavior of A is what? Ductile. Behavior of B, austerite, highly ductile. Then martensite, hard and brittle. Why I am teaching this? Because when we come across this thing in the coming lecture, you can understand what will be the property. If you are doing because each heat treatment will give you different products. So if product will change, property will change. So at that time you can correlate. Okay, so hard and brittle. Then D is perlite. Perlite is tough, basically. Or hard and tough also, you can write tough. Tough. Hard and tough. Okay. Then vanite again is interesting. It is tough. Can you tell me why they are tough? Why this vanite and perlite are tough? They are not ductile, not so having high strength. They have strength, high strength, but why I am keeping in that particular property is toughness, high toughness? Because they have their mixture of phase. One phase is ductile, one phase is stronger. So due to this mixture, they are tougher. You understand? Because Fe3C is what? Very hard and brittle, right? But ferrite is soft. So mixture of these two phases will give you mixture of the property. So it is tough. You understand my point? So then F is hard and brittle. Then G, same tough, you can write. But we don't come across ladybird because it is a phase which is above the room temperature, basically. We come across mostly ferrite, martensite, perlite. These are the phase we come across because they are room temperature phase. Vanite, cementite. So whatever heat treatment we are going to discuss, all will be there in one kind of heat treatment. Now the question is, how we can govern. Okay, why BCT structure is very very hard and brittle? Why martensite is very hard and brittle? Tell me. What is the initial structure? FCC, na, austenite. Phase always transform from austenite to some product. See, whatever the transformation will happen in this direction, it starts with austenite first. Then austenite will convert into whatever phase or mixture of phase will be there. That means austenite is the parent phase, and these are the product phases. So that is the reason why we always heat the steel above A3, upper critical temperature, or if it is eutectoid steel, then above A1, right? That is why we are doing austenitizing always first. Austenite means in a single phase, and if you cool it, it will transform into different products or different phases, right? So what was my question? Okay, my question was why BCT or this martensite is very hard. What is the reason? You have studied in phase transformation. You studied the phase transformation, martensitic transformation, perlitic transformation, spinodal decomposition. वो क्या होगा? हाँ, diffusion less. Okay, fine. Very good. अच्छा, do you remember? Okay, FCC is what? FCC is cubic. Okay, FCC is cubic. FCC is cubic, but cementite is BCT, body centered tetragonal. So you are converting cubic system to tetragonal system. What is the difference between cubic system and tetragonal? Cubic system means A is equal to B is equal to C. All the edge length are same. Shall I draw the diagram, or you remember? If you take a cube, all the edge length are same. In x-axis, y-axis, z-axis, all the edge length. But in BCT, means tetragonal structure, A is not equal to C. Right? A is equal to B is not equal to C. C means this axis. A means this one or this one. And right, A is equal to B. But this axis is actually in martensite, this axis is long. This axis is long. And this length of this axis depends upon the amount of carbon. Why? Why? Because the structure is moving from FCC to BCT. FCC means what? FCC means it is a solid solution. Everything is in solution. Right? Whatever carbon was there will remain in solution. Solution means in interstitial voids. No cementite will be there. Cementite is a precipitate, no? Cementite is a compound. That means cementite also get dissolved. When you austenitize the sample, initial sample of cementite, it will also get dissolved. So austenite is a complete single phase. Whatever precipitates, everything will be soluble in that. Right? So that means lot of carbon will be there in the FCC or austenite due to dissolution of cementite, due to everything. Lot of carbon is there, and solubility of carbon is also high in cementite, if you know, 2.14 maximum. Anyway, the moment you cool it, suddenly martensite will form. How? The moment you cool it very suddenly, it wants to become BCC, because room temperature phase is always BCC, body centered cubic. High temperature phase is phase centered cubic. Iron always lies in this, BCC to FCC, FCC to BCC. But you are cooling very fast, you are not giving sufficient time, so there will be no diffusion phenomenon. See, diffusion means what? Atoms should move, but you are cooling at a so fast rate, all the atoms will get freezed there. They will not get time to diffuse, move, right? But initial crystal structure is FCC, right? And it want to become BCC, but due to this excess carbon in the octagonal voids, in the edge length, these are the edges, no? So in the edge length, lot of carbon will be there. So what will happen if you are inserting something forcefully? This will get expanded. So there will be a lot of strain in the lattice. The lattice will automatically get strained. But if FCC will become simple BCC, there is no issue. A is equal to B is equal to C. No issue. Right? But lot of carbon is there. So automatically there will be lot of lattice strain because of elongation of this C axis. That's why we find out C by A ratio, if you remember. No, C by A ratio in case of martensite, BCT structure. Higher is the C by A ratio, higher is the hardness value. So how C by A ratio is increasing? That means C axis is getting elongated. Okay? How it is getting elongated? More carbon is there. More you put the carbon, this axis will get elongated. So C by A ratio will improve. This A will get squeezed. In one direction it will get squeezed and direction. Anyway. So final conclusion is what? Because of lot of strain in the lattice. That is the answer. Because of lot of strain in the lattice, the strength will increase. Okay? Because lot of strain in the lattice. So you understood how this is happening. Because of sudden cooling. That's why people call a martensite is a diffusion-less transformation. There will be no diffusion because you are not giving time. But if you cool slowly, martensite will never form. All the carbon atom will diffuse out from FCC and it will form BCC or cementite, BCC plus cementite. Okay? Do you understood this one? This is a very interesting thing. You should remember. And you have to remember also, this is another point. Whenever martensite form, it is a shear transformation. Do you know this term? Shear will occur. The parent crystal will get sheared up. Shear means plastic deformation is happening. So when plastic deformation happens, then what will happen? Dislocation generates. So when martensite form, lot of dislocation also forms, generates. So if dislocation concentration will be more, it will become strain hardened automatically. So these are the two things. One is due to lattice strain and another point is due to generation of dislocation. Because martensite transformation is a shear transformation. So I suggest you watch my YouTube videos on physical methods. You will get lot of information. All the information are there. Just watch it. And in those videos, diagrams are also available, so it will be easy for you. I cannot draw it right now, so it will be easy for you to visualize the thing. Anyway, so now next is how heat treatment temperature is governed. That means the first cycle of the heat treatment is what? Heating cycle. So how you can determine the predetermined temperature? We have already discussed that. You remember? We have to find out the austenitizing temperature. So for that, you have to draw the iron carbon diagram, lower part of the iron carbon diagram. Okay, you have to show the critical temperatures, then only. So in iron carbon diagram, the critical temperatures A1 or A3, they are theoretical temperature actually. Theoretical, those are temperature. But in the real situation, whenever you are doing heat treatment and you are heating the steel at a very fast rate, the actual temperature will be changed. It will not remain same. Suppose A3 temperature is 910, let it be. But you are heating the steel at a very fast rate. It will not remain 910. It will may go to 920 or may go to 930 like that. You have to remember this particular concept. So what I can write? We can govern a heat treatment temperature by looking at the iron carbon phase diagram simply. But iron carbon phase diagram will give you theoretical temperature, not real temperature. Why? If you are heating the steel at a very fast rate, the A3 temperature will rise from the theoretical temperature. It will not remain same. Similarly, if you are cooling it very fast, your A1 temperature will go down, A3 temperature will also go down. But if you are doing at slow rate, they may not be changed. Whatever actual temperature and theoretical temperature will remain same, mostly. But sometimes we need faster rate of heating and all. Okay, anyways, you should remember this. Heat treatment of plain carbon steel versus alloy steel. Okay. Plain carbon steel means what? There are two constituents in plain carbon. Plain carbon, that means iron will be there and carbon will be there. No other alloying element will be there. That is called plain carbon. Alloy steel means what? Apart from iron carbon, Some other alloying element will be there. Maybe chromium, maybe nickel, maybe tungsten, whatever, molybdenum, vanadium, whatever, depending upon your requirement or properties. Okay. So that is one of the reason why alloying addition also improves property, like solid solution strengthening. We get solid solution strengthening by adding alloying elements. It may be interstitial, it may be substitutional. Okay. Anyways, so what is the difference? Can you tell me? Okay, in case of plain carbon steel, you are at eutectoid composition. So what will be the phase, initial phase? The composition of the carbon is in eutectoid composition. So what is the room temperature phase will be there? Perlite will be there, alpha plus cementite will be there. Okay, fine. So when you are doing heat treatment, when you are taking the plain carbon steel to austenitizing temperature, there is no issue actually. Why? Austenite will form, that means ferrite will become austenite, and the cementite, precipitate, they also easily dissolve in that, completely dissolved. All the carbon will be uniformly distributed. There will be no cementite at austenitizing temperature. All will get easily dissolved. But there is an issue when you are dealing with alloy steel. So when you are dealing with alloy steel, for example, you are dealing with alloy steel having vanadium, niobium, titanium. What are these elements? They are strong carbide forming elements. They have very high affinity towards carbon. So titanium will form what? Titanium carbide. Niobium will also form niobium carbide. Vanadium also form vanadium carbides. They are very strong carbide forming elements. They have less affinity towards iron rather than towards carbon. Right? So what will happen now? Can you tell me? What changes we need to do in heat treatment? The concept is they are very strong carbides. In plain carbon steel, you have cementite as a carbide, okay, Fe3C. But in alloying elements, they are very strong, very stable. So what it means? No, sir. That means they will not easily dissolve. This titanium carbide, vanadium carbide, they will not easily dissolve. Like Fe3C is also a carbide, but it will dissolve. They will not easily dissolve. So what can be done? You rise the temperature somewhat higher. You go to a high temperature. Suppose you are going to 1000 degrees. Go for some 1100 degrees centigrade or 1150. Then it will get soluble. So that is the answer you have to remember. Whenever we are dealing with alloy steel, where alloying element forms strong carbides, you need to go to very high austenitizing temperature. That is the answer. To dissolve it. And diffusivity also matters. These alloying elements do not diffuse at very fast rate. Carbon can easily diffuse, carbon is a lighter element. Iron also can diffuse, iron is iron, fine. But these alloying elements, vanadium, niobium, titanium, their diffusivity is very slow. Sluggish, in technical they call sluggish diffusion. So what is the solution? Again you go to very high temperature. So my point is, whenever you are dealing with alloy steel, you have to go to a very high austenitizing temperature so that they will dissolve and they can also move, diffuse faster. So what happens to the holding time? Obviously it will improve. You have to keep the holding time more for alloy steels compared to plain carbon steel. Because you want to make pure austenite, a homogeneous austenite you want to form. That is the main criteria. No? That is the parent phase, always. Or in any heat treatment process, most of the heat treatment process, you have to produce a parent austenite. Parent austenite means a single phase will be there. There should not be any precipitate, there should not be anything. Only austenite. Grain boundary. Whatever initial things will be there, so all will dissolve. Is it okay? Then phase transformation will start when you cool it. This is clear, I guess. Huh? You may get a question from this also. What is the difference between doing heat treatment in alloy steel and plain carbon steel? Let's justify it. Simply write, we have to go to a high austenitizing temperature in case of alloy steel. Why? Because alloying elements diffusivity is low. Alloying elements, those from stable carbides, their solubility is also very low. It takes time. Okay, this is done. Holding time. This is important again. So how you decide holding time? Heat. Up to what temperature you understood by looking at iron carbon phase diagram, right? But how to decide how much time you have to hold?
The whole sample terms in cross.
Yeah, that's right. But how? Like, what is the thumb rule? What is the thumb rule?
Like 1 inch, 1 hour.
is okay, yeah.
Or the thickness more.
More is that is fine. Actually, you have to remember, if it is a plain carbon steel, then for 1 mm thickness, you have to keep it for 2 to 3 minutes. Suppose it is 2 mm thickness material, then 2 into 3 or 2 into 2 whatever. If it is 10 mm thickness, then 10 into 2 or 10 into 3. For each mm thickness, you have to hold it for 2 to 3 minutes. That is the thumb rule. But condition it should be plain carbon. Once it become alloy steel, you have to hold for large interval of time. 25 to 40 times improve in the holding time will be there. Is it fine? Or in easy way, some people say 1 inch thickness means 1 hour 10 minutes, plus minus 10 minutes, plus 10 minutes actually. You can convert it into inch also, to millimeter. 1 hour holding time means thickness is basically 1 inch. Okay. Is it fine? So this is the way to do heat treatment. First you check the iron carbon phase diagram, you check what is A1, what is A3. Accordingly you put the sample, then you heat it slowly or fast. Already we discussed when to go for fast heating, when to go for slow heating, already we have discussed. Then you hold it, for holding you need to check the thickness. What is the thickness? If thickness is 10 mm, then 10 into 3, that minute. Done. Then finally, how to decide the cooling rate? How you need to cool it? Can you tell me now? What kind of final products or phase you want in your steel? Depending upon your requirement, you can do the cooling rate. You can go for very slow cooling, you can go for intermediate cooling, you can go for very fast cooling, or whatever according to requirement you can do. Fine. Okay, then this is done. Okay, this one. Suppose we can have two kind of microstructures. One is equilibrium microstructure, one is non-equilibrium. What is the meaning of equilibrium microstructure? Can you tell me from the last bench? At least, CR will tell. What is the meaning of equilibrium microstructure? Or what is equilibrium phase diagram? You know, phase diagram is also called equilibrium diagram or constitutional diagram. What is the meaning of equilibrium? Iron carbon phase diagram is the equilibrium diagram or not? It is the equilibrium diagram. That means whatever the products will form at the room temperature, they are equilibrium products actually. Iron carbon phase diagram is the equilibrium diagram. How this equilibrium diagram is, how you can say it is an equilibrium? Because you are cooling the molten iron at a very, very slow rate. So finally everything will be in equilibrium at the room temperature because of slow cooling rate. But if you are quenching it, you take molten iron and quench it. Whatever product will form, those are not equilibrium products. They are non-equilibrium products. So what is the example? Martensite. Martensite is a non-equilibrium product. So you have to remember. Benite is also, sometimes people call benite, martensite. They are non-equilibrium products. And whenever there is a non-equilibrium product, your strength, your hardness will be always more. If you want more strength, more hardness, go for non-equilibrium products. If you want ductility, toughness, you can go for this equilibrium products basically. Okay. So what are the equilibrium products in iron carbon phase diagram? One is ferrite, cementite, pearlite, mixture of phase. These are all equilibrium products. And what are non-equilibrium? Martensite, benite. Okay. Anyways, you understood my point? There is another very important line. Whenever we are cooling from austenitizing temperature at a very fast rate, it doesn't mean you will always end up with 100% martensite. You sometimes end up with some retained austenite. Some austenite will retain. How it will retain? You remember MS, martensite start temperature, martensite end temperature, finish, finish. Suppose martensite start temperature is 200 degrees centigrade. You are cooling from 950. 950 means austenite. You are cooling to very fast rate of cooling. You are keeping the steel at suppose 100 degrees centigrade. Let it be. But your martensite finish temperature is room temperature 25 degrees centigrade. So what will happen? You will be having two phase now. Martensite plus retained austenite. Because you didn't cool it below 25 degrees centigrade. Do you understood or? Okay, maybe I will explain it again in coming lecture. When you are cooling the steel from austenitizing temperature at a very fast rate, and you want to produce 100% martensite, then you have to go below MF. MF is the martensite finish temperature. That means all the austenite will become martensite. But if you are keeping in between martensite start and finish, then both phase will be there. Some austenite will be there, some martensite will be there. And what will be the problem? Your end product steel will be having austenite and martensite. What is the issue in application? It may get fracture somewhere basically, because you have very soft phase and very hard phase. It may break somewhere, failure may occur, or it cannot withstand the load, because austenite is a very soft phase, very soft, FCC. Okay. Why austenite is a very soft phase? Now tell me. Why austenite is very soft? Softer than BCC, ferrite also. Why? More slip system. No, BCC have high slip system, 48. Active slip system. Austenite is FCC, it has 12 number of slip system. But BCC is 48. So more number of slip system are there in BCC. How then ductility is more?
Different direction होता है उसका.
किसमें different direction होता है?
BCC.
प्लेन एक ही प्लेन होता है.
एक ही एक्टिव प्लेन को 3 डायरेक्शन होता है. इसलिए पुट्टी कर देता है, लेकिन एक्चुअल में एक्टिव फ्री होता है BCC.
Okay, fine. Yeah, you are right somewhat. You can simply say actually in case of FCC you have 12 number of slip system, but those slip system can be easily activated. You should not say active slip system. It can be easily activated even at room temperature. That means all the slip direction are inside the slip plane and they can be easily activated. That means gliding of the dislocation will be easier. You have to provide very low amount of stress to move the dislocation. What is that called? PL stress, no? You have studied maybe. PL's Navarro stress. The stress required to glide a dislocation or to move a dislocation. No? PL's Navarro stress. It is required by FCC in a less amount. But in case of BCC, you have 48 number of slip system. But the slip planes are not so closely packed also in case of BCC. That is also important point. In FCC, atoms are very closely packed in the slip planes. But in BCC, there is some gap. They are not so closely packed. Suppose I will make you stand by touching one another. If I will just push someone from behind, everyone will fall down, right, easily. But if I will put some gap between many people, if I have to push at a very high velocity or with a very high amount of stress, then only they will fall, right? So in case of BCC, if you carefully look in the slip planes, they are not so closely packed relative to that of FCC. So less amount of stress will be required for FCC, but more amount of Pierce Navarro stress will be required for BCC. That is also a point you have to make. And like you told, so and like whatever you told, that is related to cross slip. Actually, cross slip happens in BCC also. And that in other way I can say in BCC, the slip planes or the slip, they cannot be activated easily. You have to go to a very high temperature to activate them. But in FCC, it can be easily activated at room temperature. Okay, done. So you have class. Okay, we will discuss that in coming lecture. Precipitation hardening.